In this lecture, I'm going to really talk about how we're able to identify whether a redox reaction will occur or not occur. And we're going to use something called net potentials to do that. Before we get there, we have to get to some important redox basics that really are tied to the concept of whether a reaction will occur. And we use the word spontaneous to talk about that. Okay, so let's start with copper. Now, copper we know is a very important conductor of electricity, or an element used as a conductor, and also very important because of its non-reactive properties. For those of you that know that copper is often the metal used for water or plumbing that comes into the house, and there's some good reason for that. Any case, well, copper is a metal, and like most metals, copper has ability to conduct because of its metallic bonding, but more importantly, because of its electrons are held relatively loosely. So now metals are affected by oxidizing agents. Now, oxidizing agents like to pull electrons away from the metals, and what happens to the metals is they become ions. And these ions do not have the same properties as the metal. Sometimes they dissolve, and sometimes they become an ionic crystal, as in the case of rust. We have iron, and we know its properties, and then when it gives up its electrons to an oxidizing agent, okay, it becomes iron plus 2, and it could attract and bond with oxygen -2, because oxygen could be that oxidizing agent that grabs the electrons and becomes negative. And what you have is a crystalline structure, and that's the rust, which is far different from the metal. So we know that metals undergo oxidation. Now, what makes the oxidation occur? Well, one thing is the action of acids, and sometimes we don't talk enough about this, but acids, as we all know, the action is due to the proton, okay? And as I've already mentioned to my students, a proton is like a heat-sinking missile for negative charge. Based on Coulomb's law, the radius of a proton is very small, and it's +1. So I like to say it has a high charge density. So the H plus that comes off hydrochloric acid, or the H plus that comes off of nitric acid, again, heat-sinking missiles or electron-sinking missiles that are looking to attack and get electrons. In the case of flesh or organic compounds, acids decompose organic compounds because the H plus will get electrons from the bonds between carbon and hydrogen and get these electrons and break them. So it's important to understand the action of acids, okay, is really redox. What happens is this H plus can yank electrons from the other target. So H plus is an important oxidizing agent. Now we can't forget the most important oxidizing agent in our environment is oxygen. That's where the word comes from. So the action of oxygen on metals has been known for a very long time, that this oxygen will oxidize it and make it into a different form. Just like if you had sushi, that nice tuna, that nice red color can be a grayish color because oxygen can oxidize it. So it's important you get that. So another important oxidizing agent besides oxygen is the proton. So the action of acids on metals, okay, is a redox response. So metals who hold electrons loosely, it should be understood that this H plus should be able to pull electrons away. Now, the problem is that's not always the case. This question of whether or not H plus can pull electrons away is twofold, and we'll get to that. But what do we expect to happen? We expect this H plus, which is small and +1, to grab electrons from copper, and the copper should become +2. And the same thing would happen over here. And we would expect the H plus to gain electrons to become hydrogen atoms, and that's where we get the hydrogen gas. And it's very important you understand that if hydrogen gas is being made, then my friends in chemistry, then a redox reaction has occurred. The protons have acted on the reducing agent. They themselves got oxidized, and the other elements got they themselves got reduced by gaining electrons, and the other compound, like the metal, okay, got okay, got oxidized. So I can say that. So the H plus, being an oxidizing agent, forces the electrons away from the metal. They themselves get reduced. And you know that because +1 goes to H0, charge went down, and the metal gets oxidized. Metals can only get oxidized when they're metals. Now, so we'd expect this to happen because, well, it's a strong oxidizing agent. But we have to consider the strength, okay? Oops. We have to consider how well the other chemical will lose electrons. Think with me for a second. We have copper. We know it's not highly reactive, and that's the reason why we use it as metals for the plumbing of our water into our homes. And then we have H plus. Now, if H plus is great at yanking the electrons away, that's where my little arrow here is, all right, then we'll have what we call a potential difference. Now, what I mean by that is a potential difference is a possibility that a flow of charge could happen, and that's what a voltage is. And we'll get to that in a second. But there's twofold in this process. If a redox reaction can occur, it means that the oxidizing agent, the element or ion that can pull electrons and force the oxidation or loss, Leo means loss, from the copper, is strong enough to pull them away. But it also might mean that the copper, okay, is good enough at pushing its electrons in this direction, meaning it's forcing what? The reduction onto H plus. Remember, this is an oxidizing agent, and this is a reducing agent if it likes to give up electrons. Oxidizing agents, okay, except they themselves get reduced. Reducing agents lose. So think about a push by the ones who get reduced. I'm sorry, the reducing agents. The reducing agents are pushing its electrons onto the oxidizing agents. And if you don't like any of those terms, the one who gets what? Oxidized is throwing its electrons to the one who gets reduced. Okay, so the metal is pushing its electrons, and what's happening to the H plus? It's supposedly pulling. And if we have this scenario going, we will have a voltage. Now, a voltage means that there's a place of high charge and a place of low charge. And electrons will flow, I should say charge will flow downhill to less charge. If you think with me for a while, if I was to have the same charge on both sides, would there be a flow? No. All right, if I have water of equal height potentials connected by a river, okay, the water is really going to have no current. But if I was to increase the topography or the height at which the water is coming from, it's going to flow downhill. And that's what we're talking about in terms of voltage. Voltage is the force due to the pushing of the one who oxidizes with the pulling of the one who reduces. And that's what we're talking about with net potentials. Now let's go to and look at some examples of this. Let's look at copper and hydrochloric acid. What we have here is the activity series of metals, and this is a very famous lab. And what we're going to do here is we're going to test different metals. The X is the metal and the hydrochloric is the acid. And if we have a single replacement reaction, as you may have learned, you're going to make a metal chloride. Notice the hydrogen gas that exists because the H pluses are going to yank electrons from the metal, okay, and produce the hydrogen gas. So I have tin, iron, magnesium, copper, zinc, and calcium. And what I'm doing here is I'm just pouring some hydrochloric acid, and we're looking for the fizzing, basically the identification that hydrogen gas is being made, meaning H pluses have gained electrons. So I'm pouring in the hydrochloric acid. See, magnesium is really fizzing. You clearly see that there is very, very reactive and very spontaneous redox reaction happening with magnesium. Notice you don't get that with the copper. Adding hydrochloric acid, you'd expect the H plus to pull the electrons away. Notice the zinc. The zinc is fizzing too. In fact, if you look carefully at the magnesium ribbon is gone. Look at the calcium. The calcium is, look at that reaction. Look at the amount of hydrogen being produced. And you notice what happened to the magnesium? It didn't disappear. It became Mg plus 2. And it became a what? An ion. Look how crazy calcium is. So we can see that different metals are reacting more or less spontaneous than other metals. Some not seemingly not reacting at all, the tin or the copper. Why is that? Well, it's because these different metals have different abilities to lose their electrons. Remember, for a redox reaction to occur, you have to have something strong enough to yank an electron, but you have to have something good enough to pull or push that electron along. Copper seemingly doesn't like to do what? Give its electrons to the H+, or the H+ isn't strong enough to pull electrons away. That's important. So when I pull copper up close and personal, you don't see much of anything. You don't see any example of any hydrogen bubbles existing here. There's essentially no reaction. Yet the ones behind it are going crazy, some of them. So the copper and the hydrochloric acid essentially does not have any reaction. Okay, we don't get what we expect. And the answer to this is probably the proton isn't good enough at pulling the electrons away, or the copper isn't good enough to push its electrons. Remember, it's a combination of two. How well this loses and how well this gains. So in this case, H+ is not a strong enough oxidizing agent to pull electrons away, and that's why we use copper pipes. Copper pipes are not going to corrode and become copper+2 ions and decay and have leaks in our basement if our water that is carried to our house gets acidic. Most water is acidic, and over time we'd have tremendous leaks due to that. So that's why copper is used. Now, what would we expect if we used copper and nitric acid? Okay, well, we just learned the H+ isn't strong enough. So we might expect that there would be no reaction because the H+ cannot pull electrons, and still the H+ isn't a strong enough oxidizing agent to do so. So we would probably expect no reaction here. But there is a reaction. And why is there a reaction? Because there's something called the nitrate ion. Now look carefully at the nitrate ion. Let's make some room here. The nitrate ion, let's do it up here. The nitrate ion is an N, with 3 zeros, and it's -1. And I'm just not going to write I'm not going to do a Lewis dot diagram here. It's something like this. And I guess I just did. I put the dots I won't put in, but we know that we have what? NO3 -1, -2, -2, -2. So it's -6 overall for the oxygens. The N must be +5 in order for the whole ion to be -1. So we have 3 very electronegative atoms with a +5 in the middle. That's an electron sink. Electrons are going to be attracted by the very electronegative oxygens, but then drawn in to the N+5. That's an oxidizing agent. I know we speak about the nitrate ion being a what? A soluble spectator, but it's also a very important oxidizing agent. So the NO3 -1 can cause, well, we'll see, may be able to pull the electrons away from the copper and not make hydrogen gas because the H+ isn't going to do something. We want to see what it makes. Let's see that reaction. So what I have here is I have some copper sitting in a Florence flask. Okay, and in the Florence flask, I'm going to pour some nitric acid. Now, it's not the H+, it's the NO3- that's going to be able to react with it. So the NO3-, that N+5 surrounded by the 3 oxygens is electron sink, and that oxidizing agent is stronger. Now, I'm pouring some hydrochloric acid, as you can see, all right, into it. And we're going to see that the hydrochloric acid, and this is full strength, has no effect whatsoever. There's nothing happening here because the H+ are just not strong enough to yank the electrons away from the copper. But if I was to add some nitric acid with the HNO3, what do we have here? You can clearly see a chemical reaction because a brand new substance is being made. In fact, a reddish brown gas is being produced that I'm going to push back the other side. So there you go. So I'm producing a vigorous, spontaneous reaction. Notice the color here. So we're copper metals becoming copper what? Copper ions, and this reddish brown gas is called NO2. And clearly, we've got ourselves a reaction. Now, what's really cool is that as the reaction fades, okay, and stops, this gas, which is also exothermic reaction, okay, forms a partial vacuum, and it pulls back the water. And you can see that it's pulling it back here, and I'm just going to cut to this, and there it goes. And we're going to make a siphon. So the lower pressure here is going to create a siphon, and at some point, okay, the water is going to come rushing back in, and we're going to get the color, okay, of the copper ions, which should be a greenish blue, okay, and you can see that happening here. Pretty cool. Okay, so it's a nice little reaction, and let's stop that there. So the nitric acid was able to pull electrons away. Now, what was that reddish brown gas? Okay, well, let's just clean up some things here. What was that reddish brown gas? Well, it certainly wasn't hydrogen reaction, and we do have a reaction here. What was it? Well, we noticed that the N is +5, and what it made was NO2 gas. Now think about this. O is -2. There's two of them, -4 overall. For this to be 0, there's no charge associated with the entire molecule. So 0, nitrogen is +4. Okay? So what do we have here? We have a +4. Now let's get rid of this because that really didn't happen. Okay, so we made NO2 gas. Okay, and of course we made copper +2. And there's some nitrates that aren't used. Okay, and we'll just leave that alone. We'll bounce that another day. But we made a new compound. It's a chemical reaction, and there was a flow of electrons from the copper to the nitrate ion in this case, and it was spontaneous. We saw it occur. This was non-spontaneous. We'll just know non-spontaneous. It did not occur. This was spontaneous. Now, spontaneity is a word we use in thermodynamics that says that there's an actual pathway for the reaction to go. There's a direction in the process. Now, where's the direction? Look at my arrow. It goes from the one that gets oxidized to the one that gets reduced. Why? Well, why was there a direction of electrons in this case? Because we had copper was able to push its electrons onto the NO3, and the NO3 was able to what? Pull. That pushing and pulling created a place of high charge to low charge, which we call a potential difference or a voltage. And when you get positive volts from these two half reactions, okay, you can use that energy to push charge around in batteries or to create and use it for energy. When things are spontaneous, as we're going to learn in another unit, that means that there is positive, or I should say there's a Gibbs free energy. There's free energy that can be used. And we'll get to that another day. But there's a pathway because of the pushing and pulling. We didn't have that when it was copper and H+. That was not the case because the NO3 wasn't good enough at what? Well, the H+ wasn't good enough at pulling electrons away, and the copper wasn't. The copper wasn't good at pushing its electron. Here, there's a two-pronged attack where you have copper is able to push and the nitrate ion is able to pull. And that combination gives me a voltage. And that's where this voltages come from. Now, sometimes the one that oxidizes resists. Now, copper tends to resist most often, but if I was to replace copper with, say, gold, as we know, gold is most sought after because it doesn't rust, it doesn't oxidize. It really holds on to its electrons. So we really need to force something to pull gold along. So if we're going to look at gold and think about gold's ability to oxidize, we have to think about the one who is being reduced, or the one who's the oxidizing agent has to overcome gold's ability to do so. That's important. Very important. So this voltage or net potentials we're going to get to in another lecture is the idea of this pushing and pulling along. And in the case of gold, in order to make gold oxidize, and we need something that's strong enough in pulling electrons from it that can overcome its inability to oxidize, and vice versa. I have things that don't like to get reduced, okay, but if something is so good at oxidizing, let's say like sodium is so good at pushing its electrons, it can force things that do not like to get reduced, okay? And we'll talk about those two give and takes. So the idea that we can measure with a voltage per each half reaction gives us some insight whether a reaction is spontaneous and can work or non-spontaneous and does not work. And that's what we need to know moving into the next phase. Very important.